This is the second video in the series Bridge the Gap. Okay, and in this video I'll discuss about problem number 2 suggested at the Canadian Mathematical Olympiad in 1982. All right, and here's what the problem is saying. So they say if a, b, and c are roots of the equation x to the power of 3 minus x squared minus x minus 1 is equal to 0. So this is our equation here. All right, we need to prove two things. First of all, show that a, b, and c are distinct, and second of all, show that this sum is an integer number. Okay, now let's try to see what's happening here. So how would you approach the first question? So when I look at it as I see that a, b, and c are supposed to be distinct numbers. All right, well, looking back, what do I know about the roots of a certain equation, a polynomial equation, and the relationships between them? Well, what I know is Vieta's relationships, and really not much more. Okay, so how about we write down Vieta's relationships for the roots of this equation here? So we know that the sum of the roots a plus b plus c is minus this coefficient over this coefficient, so it's actually equal to 1. Okay, we know that the product, that the sum of the double products ab plus ac plus bc is equal to minus 1. Okay, so it's equal to this coefficient, which is minus 1, over this coefficient, which is 1. And finally, abc is equal to minus this over this, so it's actually equal to 1. Okay, so this is what we know. Is this helpful in any way? Well, let's see. Okay, so how can this, okay, so maybe these roots are not distinct. Okay, what does that mean for us? It means that there are actually two possible situations. Either they are all equal to each other, so a is equal to b is equal to c. Okay, is this possible? Well, if a is equal to b is equal to c, that means if we replace b and c by a in this relationship, we get 3a is equal to 1, so a is equal to 1 over 3. Right? And if we replace a, b, and c, which supposedly are equal to each other, in this relationship by 1 over 3, we get that 1 over 27 is equal to 1. Okay? Obviously, that is false, so this, okay? So it cannot be the case that a is equal to b is equal to c. All right? What else can happen in here? The second situation that can happen is maybe a is equal to b, and that value is different from c. All right? Well, just like we did with the first case scenario, let's see what Vieta's relationships become if a is equal to b. At least that much we know. So what we get is here we get, by replacing b by a, we get 2a plus c is equal to 1, right? So 2a plus c is equal to 1, which means that, for example, c is equal to 1 minus 2a. Okay, so this is a nice relationship, probably it's useful for us. Okay, now what do we get if we replace b by a in the second relationship here? What we get is that a squared plus 2ac is equal to minus 1, right? So that implies, based off of the first relationship, that a squared plus 2a times 1 minus 2a is equal to minus 1. Is equal to, yes, minus 1. Okay? So now if we work a little bit on this algebra here, we get a squared minus 4a squared, so minus 3a squared, okay, plus 2a plus 1 is equal to 0. Right? So we get a nice quadratic equation. We can easily solve it. So basically what we get here is that a is equal to 1, or a is equal to minus 1 over 3. Well, okay, well, but now if we take a equals 1 and we plug it in here, we clearly see that that's not a root of our equation, neither is a is equal to minus 1 over 3. So it's not possible that a is equal to b and it's different from c. All right? So conclusion of these two discussions here is that a is different from b is different from c. So roots are different from each other. Okay? So very nice. Let's see how we can continue this. All right? How do we tackle number 2? Okay? Well, I look at this and it's fairly complicated. These powers here, 1982, well, it's kind of a coincidence. It's exactly the same year of the contest. So they do this quite a lot. So probably 1982. Who knows? Maybe it means something. Maybe it doesn't mean anything. Okay? Maybe there's nothing special about 1982. All right? How do we get some understanding of this sum here? Okay? Well, let's remember that a, b, and c are roots of this equation. Okay, what does it mean? It means, for example, that we plug in a for x in this equation and we get a to the power of 3 is equal to a squared plus a plus 1. Okay, well, how do we get from this to this? Obviously, we are not even close, but if we actually multiply this relationship by a to the power of 1979, okay, we get the following. We get that a to the power of 1982 is equal to a to the power of 1981 plus a to the power of 1980 plus a to the power of 1979. Is this very helpful? Well, maybe it is, okay, because here's what we can do now. Okay, let's take on this only the first fraction. See what we can do with it. Okay, just because we don't have that much space and I really want to fit the entire proof in one page, even though we may skip some details. Okay, so a to the power of 1982 minus b to the power of 1982 over a minus b becomes, okay, let's write this equality here, becomes a to the power of 1981 plus a to the power of 1980 plus a to the power of 1979, okay, minus, and we get the exact same relationship but with b in place of a, because b is just another root of the same equation, right? It's going to be minus b to the power of 1981 minus b to the power of 1980 minus b to the power of 1979. Everything over a minus b. Well, is this helpful? Because from what I see here, this fraction actually looks more complicated than what we started off with. But actually, what happens is, instead of having 1982 here, we have 1981, 1980, 1979. So we kind of got a recursive relationship, okay? Because if we put together this term and this term here, okay, over a minus b, we see that we get exactly the same relationship here, but instead of having 1982, we have 1981. And if we put together this term with this term here, we get exactly this kind of relationship, but with 1980 instead of 1982. All right? And finally, if we do it with a to the power of 1979 minus b to the power of 1979, we get again this relationship. Okay? So this makes me think, well, I need to set up a recursive relationship here. Okay? So basically, what you can do is the following. For example, if we call this, let's say, x 1982, all right? Then the corresponding differences for 1981 we call as 1981 and so on and so forth. So basically, if we call xn to be a to the power of n minus b to the power of n over a minus b, we can generalize this equality by saying, okay, xn plus 3 is equal to xn plus 2 plus xn plus 1 plus xn. All right? Well, actually, I like this much better because we get a relationship that has nothing to do with any 1982, 81, 80, and so on. All right? So now what we can do is we can take it one step further. And let's say if we say let Sn is a to the power of n minus b to the power of n over a minus b plus b to the power of n minus c to the power of n over b minus c plus c to the power of n minus a to the power of n over c minus a. Okay, using this simple relationship here, okay, we can infer the fact that Sn plus 3 is equal to Sn plus 2 plus Sn plus 1 plus Sn. All right, so this is actually a very nice, very simple relationship that we got just by exploiting the fact that this equality is true for any of our roots a, b, and c. Now, how do we prove this? Well, okay, so now I'm thinking if Sn is an integer, and if Sn plus 1 is an integer, and if Sn plus 2 is an integer, then by induction it would follow that Sn plus 3 is an integer. So all the student needs to do from this point on is set up a mathematical induction claiming that Sn is an integer. Okay, now just because of the fact that there is this recursive relationship that depends on 3 previous terms, it's not going to be enough to prove that S1 is an integer. We also have to prove that S2 is an integer and S3 is an integer. So prove these 2 relationships that can be easily done by using Vieta's relationships. All right, again, basic knowledge. And then set up your induction, which is going to be no problem, and the work is done. All right, so what are the tools that we use to solve this problem? First of all is Vieta's relationships. Very nice, very simple relationships, very useful in our problems. And then second of all is mathematical induction. And the third tool will be some creativity. All right?